So in kinetics, kinetic expressions are looking at the speed at which a reaction occurs. We have our basics here that set up an expression that either you have a zero order, first order, or second order type situation. That the rate, which is a molarity over a time. Molarity over time. A change in molarity over a change in time is equal to some constant times the molarity of the reactant. Molarity of the reactant either at 0 or 1 or 2, meaning that if it's at 0, the rate is occurring at a constant speed regardless of how much concentration we have. That's not often the case, but occasionally something will not play a part. In a first order scenario, it's recorded at a 1-to-1. So the rate will go as fast as the related to the concentration, meaning as concentration decreases, we're going to have a decrease in rate. And second order means as concentration decreases, the rate is going to be decreasing at a much greater rate. These often deal with molecularity of atoms bumping into each other during the rate determining step. So one atom means just one atom needs to decay. The second order means two atoms need to bump into each other in order for this to react. Zero order means this guy doesn't play a part. But first thing we can do is a real simple thing where we compare the rates. Compare the rates. If I have going NO2 to NO2 goes to N2O4, and I look at the rate. If the rate of NO2 is equal to 2.219 molarity per second, what would the rate of N2O4 formation be? If the rate of decrease of NO2 is 2.219 molarity per second, what is the rate of N2O4? Well, the idea here is that we could look at this as rate A over its coefficient is equal to rate B over its coefficient. Well, in the case, rate A is 2.219. Its coefficient is 2. So that's equal to rate B over its coefficient, 1. So our rate of N2O4 would be 1.1. Let's see, it's 95 molarity per second. Meaning this is being formed at a slower rate because NO2 has to decay twice as fast to make N2O4. From there, but this is separate from all other things kinetic that we will look at. But one major thing we'll look at kinetics is looking at larger problems, like looking at actual data to determine a rate law. If I have A plus 2B goes to C, and I have some reaction 1, reaction 2, reaction 3. A is 0.1, we have 0.1, and we have 0.3. And B is 0.1 and 0.3 and 0.1. And our rate, we have to say, and the rate is, say, 2.8 times 10 to the negative third. And I'm making these numbers as I go, so give me a minute. And so this rate would be 8.4 times 10 to the negative third. Now, when we're looking at actual rate law, the actual coefficients do not matter, because this is the total overall reaction. This does not necessarily match the mechanism, in that this could be a multi-step reaction summarized as one overall equation. And the rate law would show that. So how do we look at this? We're going to compare two reactions where one thing stays the same. We're saying that rate equals K times A to some number and B to some number. And we're going to compare two reactions so that A stays the same on one of them and B stays the same in the other one, and look at how this is affected by the order. So in this case, rate, if I compare 1 and 2, 8.4 times 10 to the negative third over 2.8 times 10 to the negative third equals K over K, 0.1 over 0.1, 0.3 over 0.1. So this 1 over 1 cancels out. K over K cancels out. So we have 8.4 over 2.8 is 3. 3 equals 3 to the n. In this case, it's obvious. N must equal 1. If I compared 1 and 3, you would get the same result. 8.4 times 10 to the negative third, 2.8 times 10 to the negative third, K over K, 0.1 over 0.1. So 0.3 over 0.1, M, 0.1 over 0.1, sorry, to the first. Those cancel out, those cancel out. You would get 3 equals 3 over M. M is equal to 1. And from there, we plug this back into our original equation, which is a rate equals K, A to the first, B to the first, and then would find what is our rate constant K. Find what is our rate constant K. So we could plug any result. We can plug 8.4 times 10 to the negative third, K, 0.1, 0.3. 8.4 times 10 root negative 3 divided by 0.1 divided by 0.3, you would get K is equal to 0.28. Now, these don't have to be 1. What would happen if this was 9 and this was 3? If this was 9 and this was 3, then the order would have to be 2, because 3 squared would give us 9. If this was 1 and this was 3, then the order would have to be 0, because any number to 0th power is equal to 1. So we have to look at actual data and compare. This could be as complicated or as easy as you like, because you always keep only one thing changing at a time. We're always going to compare two reactions where only one thing changes and look at how the order will change. And that is how you deal with rate law data.